So what can you tell us to, not be discouraged, to continue on the path of continuous higher education and becoming that?
Well, the simple answer is I think the only things worth doing in life are hard. Like, oh, I could walk down these stairs. Oh, I did it. Like, but that wasn't hard. Who cares, right? But if you're going to climb Mount Kilimanjaro, that's hard, and that makes it worth doing. So math is hard, and that makes it worth doing. Also, if you're miserable doing math, you don't have to continue doing math. Like, math doesn't have to be a one-track path to learn math to become a math professor. You can learn math for as long as you want and be like, well, that was fun, do something else. And that's totally fine too. So, I think it's up to you, and do you enjoy the hardness or do you not enjoy it? And it's okay if you don't enjoy it. And it's also okay if it's hard and it's scary, but it's hard and that's why it's worth doing. Yeah. Is there a question back here? They would be the inverses of each other. So in a group, we have multiplication, but you also have multiplicative inverses. So you're not going to flip it this way, but you're going to flip it this way. And then if you stack those together, you could just untie, you could just like pull it, and it would just become straight. Excellent observation. Yeah? No, I love that idea. The sort of like, can we take a long, hard problem and break it into a series of shorter problems? But no, that's not going to work, at least not for the question of whether two braids are the same. Because perhaps, so let's see, what's the way to see this? So we have these rules for how to change the spelling of the words, right? So those relations between the variables that you can swap out. Perhaps at the beginning, the braids look very different, but there's sort of a lot of swapping you can do down here that can change and change and change and ultimately kind of come back up and then make them the same again. So yeah, so you really need the whole braid. Just one piece of it isn't going to be enough. But I love that idea, though. Like, you should always be thinking about, can I take a long, hard problem and break it into smaller, easier chunks? That's absolutely the right thing to think about. That is also a very good question. In this case, we mean exactly the same matrix. But there is a notion of equivalent representations. So that would be the idea of like choosing a different basis for your vector space. And so your matrices might look super different over here and over here. But if we pick one representation and we pick a basis, then we're sort of using exactly the same translation process to convert one braid and the other braid. And then we can just straight up compare the output matrices. Not up to equivalence, just actually equal entries. Yeah?
Would there be any like reasoning behind them? Like what you were thinking, see if they're the same then?
I don't know. Yes? That sounds like a great research project for you to do. I don't know. I mean, I think there's tons and tons and tons of good questions to think about, and you're thinking like a mathematician of, what would be an interesting question? And I think the interesting part of that is, what meaning are you looking for? And so if you can turn a question into like a meaningful thing about braid groups or about matrices, then yeah, that's the road. Yeah. Yeah, you're absolutely right. So there's a ton of applications of braid theory and knot theory in general into biology, and they might use this, they might care about different properties because there you're going to be modeling like DNA or polymer tangling. And so you really are limited by physical restrictions and how much can a polymer bend, what are the sort of angle measurements and stuff. And there's tons of applications there, and like they would care about sort of more rigid structures than we've built into our model. One thing I might just mention, I don't know if we have time, but one huge application of braid theory, sort of in the way that I've described it to you, is in quantum computing. So one way to build a topological model of a quantum computer is to use a unitary representation of a braid group. I just said a bunch of words. Okay, but a unitary representation of the Birao representation is one, in fact. It means the matrices that you look at have a unitary property. So we can say a matrix is unitary, that has a mathematical meaning. But one model of a topological quantum computer is you have these little points. So you have this like very thin, I don't know what, silicone something? I don't know, you have a thin thing with these particles that are called non-abelian anyons, and they're very, very sensitive. And they notice if you swap their places or not. And so that's kind of the idea of like the robots dancing around, you swap these places. And so over time, when you're doing a computation, you're swapping these anyons around, you're building a braid. And so if you want to read off a computation, you're going to use a representation of that braid to read off a matrix from the input. So there's tons of cool stuff you can do with braids, whether you're interested in more like real world biology or more like computation, quantum computing. And I think Mina said there's some like cryptography stuff you can do with it. There's all sorts of interesting things. So, yeah. I do believe we're about out of time. But I'll be here all weekend. Ask me questions. Be my friend. Also, you should make dance videos. Huh? Yep, that's Darwin.